pumps are all around us. A refrigerator is a heat pump, just like our air conditioner. These two are the same technologies. And typically our air conditioners here in Houston, average life is around 12 years, just because of our extreme heat and what we expose that equipment to. A refrigerator is the same thing, same technology, everything's the same. Most of our refrigerators, we change them because we want to change the color or some other feature. The reason a refrigerator lasts so long is because it sits in the 72-degree room year-round. It never gets exposed to the extremes that an air conditioner does. So basically, by taking our air conditioners and burying them in the earth 300 feet deep, we're basically putting them in a 72-degree room year-round. So if you look at the life of a geothermal unit versus the life of what we typically use for air conditioning our buildings, you're going to get probably 3 times the life out of them. Keep going. So the benefits are you get this utility reduction. There's no burning of gas on the site. This is an all-electric technology. You reduce both your KW and your KWH, 50% savings we talked about versus air-cooled, decentralized design. That's for big commercial buildings where you put multiple units based on how you use the space. So you don't stick a big 40-ton unit on 30 different kinds of rooms that might be all different space types, like maybe in a hospital. You got patient rooms, you got surgery rooms, you got all kinds of rooms that are used differently. You don't put one unit to serve multiple types of spaces. You put a unit for whatever that space need is. Keep going. So here's inside components. A vertical unit, if you've got a vertical in a closet, if you've got a mechanical room, or sometimes some of these attics are big enough you can stand one in the attic. Horizontal units to replace the horizontal furnaces like most of us probably have in our houses up in the attic. Console units, typically in classrooms, hotels, things like that, for replacing the old PTAC units that stuck through the walls underneath your hotel room window. They have this vertical stack unit. I call it the Marriott unit, because if you ever go in there in Marriott, there's a box out in the middle of in the corner of the hotel room. The thermostat's on that box out. In behind that is typically a geothermal unit. And they may tie it to a cooling tower or something like that, but it's a water-cooled air conditioner. Keep going. Rooftop units. I put a lot of these on McDonald's and fast food restaurants, things like that. Water-to-water units, what you use for making hot water for swimming pools, domestic hot water. You can make chill water, hot water, all kinds of applications. Outside air units for conditioning, but 98 degrees outside before it gets thrown into a 72-degree space. Keep going. Split systems in the upper left, like what most of us have in our houses, where you have an outdoor unit. If you're trying to do a change out, rather than try and drill all the wells and get that piping into the house, you can set a condenser out there, reuse the refrigerant lines. The latest technology is VRV, variable refrigerant volume, where you have a single unit, and it's probably hard to see, you've got different kinds of units. See the one hanging on the wall here, mounted on the ceiling, stuck in a T-bar, another console unit, different kind of console unit. And then all of these tie together with refrigerant lines back to a central condenser, kind of like a chilled water system, but you're using refrigerant as the means of gathering heat from 4 different people to take it to one place to put it in the water. Keep going. So typical vertical geothermal heat exchangers, you got the vertical, which we would do in most of our houses in Houston. Most of the office buildings will do this. Keep going. Horizontal loops, if you've got a rural community or you got a whole bunch of land, it takes about 3 times the land area to do a horizontal loop as it does a vertical loop. And for most areas of Houston, because our drilling is relatively cheap, what it costs you to do a horizontal loop with a backhoe, if you have to pay for somebody, you can almost get it drilled for the same price and have a whole lot less exposure to the land. Keep going. Pond loops. any body of water, with maybe a retention or detention pond. I've got a bunch of these up in Lubbock, where they use those stormwater collection ponds. One up in Dobbin on a house. There's some scattered throughout. You can do those on the Gulf Coast. I got one on our Parks Department in New York. Keep going. Open loops, where you actually use the groundwater. This is another technology where you pull the groundwater out, run it through the system, put it back in a lake. You can drill another injection well, put it back into the groundwater. It'll just be warmer. Keep going. Now here's a bunch of pictures of what you can see where they come in with a drilling rig, drill a hole, load the loop in the hole, tie all the pipe together with heat fusion, and then you end up with your supply and return lines. You can tell this is the corner of a mechanical closet. This is probably the floor drain once they cut it off. So they set the unit right here, tie it to the geothermal pipes, run the condensate into the floor drain, and run the ductwork in the building. So there's nothing that sits outside. Everything outside is below grade. So it's a whole lot cleaner application around the building. Keep going. So once you've drilled all those wells, and you can see them up here in the upper left, it's like 2 rows wide, it wraps all the way around that building. You dig down, you tie them all together in parallel, then you fill them full of water. I'll show you another picture of that, I think. And then once you're done, you grade it over, let the grass grow back, and you never know it's there. Go ahead, Ralph. Here's your ports where you came, this particular job, it came in the building. You got your service valves for filling it full of water. You got your 2 pipes running down the hallway. Here's a unit in the hallway. Here's a unit. This is a dormitory at a college campus. Every dorm room has a little unit in it. So every dorm room can have heating or cooling on call as they want it. Hook your ductwork up to it. Here's a project well known, the Oklahoma Capitol building. There's like 600 heat pumps in that building. Keep going. So a hybrid system. If you get a really large application, this is typically the way you do it. You size the ground loop to provide 100% of the heat. Go one more, I think it's going to have another slide. And then for cooling, you put enough heat in the ground to get you through the winter, and then you reject the rest. From a capital cost standpoint, if you've got a whole lot of cooling going on, this is one of the most cost-effective ways to do it. Here's a small cooling tower on a house where they put enough loop in for the house and then a cooling tower to shed the excess heat with a little pump box beside it. Residential tax incentives, much like the solar one, you get to write off 30% of what you spend. It's got a whole bunch of language in it. Get a tax guy to tell you about it. Go to the next one. They did the same thing for commercial. Structured a whole lot different. You need a tax guy to get through all that. But there's a whole bunch of rebates, just like your solar. They almost match the solar thing equally for geothermal. So here's a bunch of, let me, before we start this, now that we've got this tax incentive that came out a couple of years ago, this year there's a whole bunch of new people entering the market that are now being called thermal utilities. And they're coming out and building the ground heat exchanger, because that's basically the cost difference between normal air conditioning and geothermal. They're putting the loop fields in for free on their dime and then selling the heat in both directions in and out of the earth to pay that back. So there's a whole bunch of companies starting up now that are becoming thermal utilities and selling the heat off the ground to and from to help pay for that. Here's a case study of 2 basically identical buildings. The one on the left, if you look through the porte-cochere here, you can see the rooftop unit over there. The one on the left is a typical VAV system. The one on the right is geothermal. Go ahead. This shows you got a 15,000 square foot building. You can see the rooftop units on the left here. One more. Here's the geothermal building, nothing on the roof. everything's below grade. You get a 55% difference in operating cost, even though you're like 25% bigger building. They got a 55% operational savings. Keep going. 47% site energy. Keep going. 28% carbon emission. Here you can see the load profile, the energy use profile. The one on the red line, of course, is the rooftop unit. The green line is geothermal. So if you're doing PV or wind, if you get your load profile to be as flat as that green line, and once you apply your PV or wind or something to it, your output profile looks almost the same as your usage profile. If you had to put a PV or wind on the top building, you've got a huge, like 47% difference between the low and the high that you're trying to figure out how you're going to bridge. The bottom one, you've got about a 5% variation in your usage. So this technology lends itself well to putting PV and wind and renewable technologies on, because it will lay the curve over and make it equal to your production rate typically. Here's the two buildings, so you can see that they are basically identical buildings. You can see they're used identically because the curve is the same. The difference between those two is the energy savings. That was in Oklahoma. Here's one in Panama City, Florida. 1, 2, 3, 5 different schools. The blue one's geothermal. The yellow one's chiller, boiler, gas heat. The red one is electric heat with a chiller. The light blue is geothermal, and then this purple is an open loop. So these two blues are closed loop, and then the purple's an open loop. We're actually using groundwater. Yeah. Yeah, I think you're almost done. You've got like 2 slides left. That shows you what the load profile looks like. Keep going. Here's a fast food restaurant, a McDonald's. 2 of them identical, about 4 miles apart. You can see the difference in the profile to apply PV to. This one's a 13% variation versus 47%. Keep going. And then there's all the people you can call to get this done. Good deal. I tried to cover that as quick as I could. Any questions?